Have you ever wondered what happens when we stare too deep into reality? Our curiosity slices past atoms, molecules, and light itself. At first, everything feels measurable, predictable, explainable. But keep zooming in, and something unsettling happens. The rules begin to bend, the picture starts to blur, and the closer we look, the less we truly see. Scientists once believed we could divide the universe forever, that matter was infinitely detailed. That observation was harmless. Yet, the deeper we peer, the more energy we need. And that very energy twists the space around what we're trying to see. It's as if nature hides a final secret behind a shimmering veil, daring us to keep pushing until our own tools collapse under the weight of the unknown. The deeper we look into the universe, the more power we must unleash just to see. But energy isn't innocent. It bends the very fabric of space and time. Every photon we fire, every collision we force in a particle accelerator carries a cost. It distorts what it touches. Einstein revealed that energy and gravity are inseparable, that too much focus can tear the stage we're standing on. Imagine trying to glimpse something so tiny that the act of looking folds the universe into itself, creating a miniature black hole that devours the answer before it's found. This is the paradox of observation. The closer we peer, the less we can truly know. Physics turns against us, warning that nature defends its deepest secrets, not with walls, but with gravity itself. The moment our curiosity burns too bright, the universe bends to protect its mystery, reminding us that every act of discovery casts a shadow we cannot see. At the smallest scales of existence, two great forces clash like rival gods: quantum mechanics and gravity. Quantum physics tells us that everything can be known, if only we can measure it precisely enough. But gravity whispers a warning. Look too closely, and the universe folds itself shut. The deeper we push, the more these laws rebel against each other, as if reality itself refuses to be pinned down. This battle between the infinitely small and the infinitely massive is the most dangerous war in science. A war fought on the edge of knowledge. When we try to measure something beyond a certain limit, the energy we use to probe it pulls space-time so tight it collapses into nothingness. Scientists call this generalized uncertainty principle, a haunting idea that combines Heisenberg's law with the crushing hand of gravity. It means there's a cosmic boundary, an invisible line where certainty dies and curiosity becomes chaos. Beyond that threshold, even the laws of physics start to tremble. At some point, even the universe whispers no further. That boundary is known as the Planck length, a distance so unimaginably small that below it, the very idea of space and time stops making sense. It's not just a measurement, it's a warning. If we could somehow shrink ourselves down to that scale, we wouldn't find smooth fabric or neat geometry. We'd find chaos. Space-time itself would boil and twist, forming what physicists call quantum foam, a restless sea where reality flickers in and out of existence like static on a cosmic screen. It's here that gravity and quantum mechanics merge into pure uncertainty, where location and motion no longer mean anything. Down there, the universe doesn't flow, it trembles. What we once thought of as empty space is alive, foaming with creation and destruction billions of times each second. And in that storm of instability lies the ultimate limit of observation, the place where the universe hides its final layer, a frontier guarded not by distance, but by the trembling edge of reality itself. When scientists reached the Planck frontier, they didn't stop. They built new theories to cross it. At that edge of existence, a new question emerged. What if gravity itself is quantum? This idea sparked one of the greatest quests in human history, the search for quantum gravity, the missing key that could unite all forces into one grand truth. For decades, physicists have tried to merge the smooth curves of Einstein's relativity with the restless uncertainty of quantum mechanics. Yet both refuse to coexist peacefully. It's like trying to draw a perfect circle with shaking hands. The closer we get, the more unstable the universe appears. But out of that instability came bold theories, mathematical dreams that try to stitch together what reality keeps apart. They all chase a single goal: to reveal what lies beyond the veil of the Planck scale, where the known laws dissolve. Somewhere in that chaos may lie the answer to everything: why matter exists, why time flows, and why the universe can spin forever without ever slowing down. In the chaos of the Planck scale, one idea rose above the rest, a daring theory that claims everything, from atoms to galaxies, is made of tiny vibrating strings. String theory transforms the universe from a collection of particles into a cosmic symphony, where every vibration becomes a note in the song of existence. What we call electrons, protons, or even light itself might just be different melodies played on the same fundamental strings. And hidden within those notes lies gravity itself, emerging naturally from the rhythm of their motion. But there's a catch. This elegant theory only works if reality has more dimensions than we can see. 10 or maybe 11, curled up so tightly that they escape detection. Imagine a universe layered like a vast instrument, each string vibrating through unseen dimensions, shaping the very fabric of matter, energy, and time. Some physicists even believe these extra dimensions could hold countless universes, each with its own rules and constants. A multiverse, where reality itself branches infinitely. If that's true, our entire cosmos might just be one verse in an endless song we were never meant to hear. But not everyone believed the universe was made of strings. Another vision emerged, one that stripped away vibrations and replaced them with loops. Loop quantum gravity, or LQG, sees reality not as a smooth fabric, but as a vast web of interlocking rings, tiny loops of energy woven together to form the structure of space itself. In this model, space and time aren't continuous. They're quantized, built from indivisible chunks, like digital pixels of reality. Each connection between these loops defines distance. Each knot defines geometry, and together they create the shape of the universe. What's breathtaking is that according to LQG, space can exist without matter, meaning that geometry itself is fundamental. It also rewrites our story of creation. Instead of a single explosive birth called the Big Bang, it suggests a big bounce, a universe that collapses, compresses, then rebounds. Theories alone aren't enough. The universe demands proof. So scientists turned their eyes to the cosmos, searching for signs that space-time isn't as smooth as it seems. Satellites like WMAP, Planck, and Fermi now scan the heavens, decoding the faint afterglow of the Big Bang and the light from distant gamma-ray bursts, tiny messengers that may carry the fingerprints of a quantum universe. If space were truly made of loops or vibrating strings, those signals might arrive fractured, delayed, or twisted in subtle ways. But so far, the results whisper only silence. The fabric of space-time appears seamless, smooth beyond comprehension. Yet the absence of evidence doesn't mean the absence of truth. Just because we can't see the quantum threads doesn't mean they aren't there. Perhaps our tools are still too crude, our reach too short, our curiosity too fragile. Every observation brings us closer to the invisible. But what if space and time aren't things at all, just illusions born from something deeper? A growing idea among physicists suggests that space may emerge from quantum information itself, from invisible relationships that connect everything in existence. Instead of being a stage where matter performs, space could be the product of the performance. Imagine a web of pure information where the geometry of reality arises from the way particles exchange data, not from physical distance. In this view, the universe isn't built from atoms or strings. It's built from connections, and the strength of those connections determines what we call space, time, and even gravity. Entanglement, Einstein's spooky action at a distance, may be the thread that sews the cosmos together. Every quantum link adds a stitch to reality's fabric. The universe doesn't simply exist. It's being computed moment by moment in the ultimate act of creation. At the end of this long descent into the unseen, we find something unexpected. Not an answer, but a boundary. The closer we look, the less we find, as if reality itself dissolves beneath our gaze. But this isn't failure, it's revelation. The universe may not hide its truths. It may simply be telling us that some truths cannot exist without mystery. Beyond the Planck scale, beyond strings and loops, beyond the trembling foam of spacetime, there may be no things at all. Only relationships, only information, only patterns of possibility flickering in and out of being. What we call knowledge may just be the language the universe allows us to speak, while its deeper story remains written in silence. Yet in that silence, wonder survives. Because every boundary we reach, every limit we hit, reminds us that existence itself is an act of defiance against nothingness. The universe isn't just spinning, it's becoming endlessly, beautifully, chaotically alive. And maybe the greatest discovery isn't what lies beneath reality, but the realization that we're part of the same mystery we're trying to solve.